Welcome to EEE 204 Lab 4. In Lab 4, we will learn about series resonance in AC circuits. To learn about AC circuits, at first we need to know by which circuitry we can implement this series resonance. We can implement series resonance by simply using a series RLC circuit. So, in our circuit there will be a simple resistance, a capacitance and an inductance. As we can see in this circuit, the source is a simple AC voltage source of 2 volt, and we have used a capacitor of 0.22 microfarad, and we have used an inductance of 2.7 millihenry, and we have used a resistance of 10 ohm. Now, by implementing this circuit, we will see how can we achieve series resonance. At first, we will learn about the different inductances, different reactances and impedances of this circuit. So, as we can see here, we have an inductance. Now, the reactance of an inductance can be expressed by XL equal to omega L. Now, we know omega is equal to 2 pi f. So, we can express XL as 2 pi f into L. Now, if we plot this as a function of frequency, so in x axis we are plotting frequency, we are varying our frequency, and in y axis we are plotting the value of XL. Just by looking at this equation, we can see that when frequency increases, this 2 pi fl term will increase, and just by looking at the resemblance with y equal to mx, we can say that this XL is equation relationship will be a simple straight line. So, our graph will look like this. So, when we plot XL versus frequency, the graph will look like a simple straight line. Now, we have a capacitance here. So, we can also determine our capacitive reactance, which is equal to 1 by omega C. Now, by using omega equal to 2 pi f, we can express this by 1 by 2 pi fc. Now, this is equation of a hyperbola y equal to c by x. This equation is a hyperbola, and if we plot this, the graph will look like something like this. So, when the frequency increases, then the value of xc will decrease. Just by looking at this equation, you can see that when the value of f is low, xc will be higher, and when f is high, the value of xc will be lower. So, we can yield this graph by varying our frequency. Now, look at this specific point. At this specific point, the value of the magnitude of XL and the magnitude of XC is equal. Now, if we express the whole impedance of this circuit, it will look like something like this: R plus J into XL minus XC. As you are already familiar with the phasor form of voltage, current and impedance, you should know that the impedance of a simple RLC series circuit is Z equal to R plus J into XL minus XC in phasor form, obviously. So, now at this point, this specific point, the magnitude of XL and XC is exactly equal. Now, if we take this value and put it in this equation, then we will see that this XL and XC will be cancelled by each other. So, our total impedance will be only the resistance. So, at this specific point and at this specific frequency, the value of Z will be minimum, because there will be neither capacitive reactance nor inductive reactance. So, the overall impedance will be the lowest. Now, for this specific frequency, we have yielded a minimum Z. Now, we already know that the current through this circuit, this series circuit, I will be simply the supply voltage by its total impedance. Now, for the minimum Z, we will get a maximum current. So when at which specific frequency, when XL will be equal to XC, then Z will be minimum and eventually I will be maximum. So now if we plot directly the current as a function of frequency, at first the impedance is something higher, and at a some specific frequency f naught the impedance will be lowest, so the current will be highest. So our graph will look like this. Now these graphs are shown in this slide. We can say that, you can see that this red line is XL and this one is XC. Let me choose a different color. This is XL and this is XC. So we can see that at a specific frequency Fr, the value of XL and XC are equal. So at this specific frequency our impedance will be lowest, and for this specific frequency our current will be eventually highest, because current is simply voltage by resistance, and as the impedance is lowest the current will be highest, and that current is denoted by I max. So in our experiment we will implement this specific series RLC circuit having this specific values. Then we will do an AC analysis. We will do an AC analysis, that means we will vary our frequency. When we will vary our frequency, we will plot the total voltage drop across this resistance, and we will also plot the current flowing through this series circuit, which is denoted by I. So we will plot I and the voltage across our resistance, which is denoted by VR. So by plotting I and VR, we will achieve a graph looking like this. So this will be our experiment, and in your lab report you will need to include these parts: objective and brief theory. Then you have to provide the circuit which will be used by us. Then you will have to provide the data, which is I max, so the maximum current, the minimum impedance, the value of XL, value of XC, and value of VR. This data should be in your lab report, and the graphs of VR and I should VR versus F and I versus F should be in your lab report, and finally you should include a simple discussion part. So this is the theoretical aspect of this experiment. Now we will learn to implement this experiment in PSpice schematics.